My name is Hallie. I'm a first-year medical student and an MSc candidate at Laurentian University. My presentation today will be on investigating dose rate effects in lens epithelial cells to understand the risk of radiation-induced cataracts. What do you think of when you hear the word radiation? There were probably some of you who thought of the classic radiation symbol, some sort of warning to stay away. You may have thought of the atomic bombs from World War II, like this image from Hiroshima. Maybe you thought of the nuclear meltdown in Chernobyl. There seems to be a common thread here, and it's not a good one. But instead, if I were to ask you, what is radiation, you may be more unsure. Radiation really means radiant energy, a type of energy that's carried in waves of different sizes. If we watch this molecule of energy move, as it gets to higher energy waves, it speeds up. You're most likely aware of radiation and don't know it. Low energy radio includes radio waves that are used by cell phones, microwaves, and the infrared rays TV remotes use to communicate. It also includes light. The higher energy waves include ultraviolet rays from the sun, X-rays for medical purposes, and gamma rays that are used in nuclear fuel. The reason radiation gets a bad rep is because if the energy is high enough, it can move small pieces of molecules called electrons that cause damage to DNA. This is known as ionizing radiation. But this type of radiation won't cause damage all of the time. It can only get through certain materials, and it loses energy as it does. So when are we exposed to ionizing radiation? The answer is all the time. Radiation sources are split about 50-50 from natural and man-made sources. However, the majority of people are not undergoing medical scans on a daily basis, so natural exposures make up the vast majority, about 98%. Natural radiation itself comes from four main sources: the inhalation of radon gas that is produced as the element uranium decays in the ground, cosmic radiation from outer space, internal radiation from the potassium and carbon in our bodies, as well as terrestrial radiation from the Earth's crust and materials used to make buildings. Okay, but how much are we getting? Let's put these into perspective and compare some dosages. First, the classic example of radiation you get from eating a potassium-filled banana. What's 200 times greater is a dose we get from sleeping next to a partner for 1 year and being exposed to their internal radiation. Pilots and flight attendants are exposed to a dose 30,000 times greater by being closer to cosmic radiation and space. And almost 2 million times greater is a dose a heavy smoker gets each year as the components of cigarettes decay in their lungs. If those are the natural exposures, when do we encounter human-made exposures? The majority of man-made exposures are linked to diagnostic procedures. This involves imaging such as X-rays and CT scans, as well as radiation treatment for cancer therapy. After that, 6% comes from consumer products that contain radioactive substances, 1% is linked to occupational exposures, so radiation technologists, for example, and the other small components come from radiation generated from the nuclear fuel cycle and finally from nuclear fallout. Putting these into perspective, I'll be comparing to the amount of radiation we get from a dental X-ray. Chest X-rays give a dose 4 times larger than a dental X-ray. A nuclear power plant worker is exposed to 60 times a dental X-ray in 1 year, and the average dose from a single CT scan is over 2,000 times larger than a dental X-ray. And to put this all into perspective, these are how the two categories of doses compare, with green being the natural exposures and blue the man-made. So am I saying that getting a head CT provides a quarter of the radiation damage that smoking does? The answer is no. This is an example of a time radiation can become misunderstood. The dose received from all of these examples I provided are well below that which would cause damage. So what would? It would take one huge dose at 20 million times larger than a banana to induce even the basic radiation sickness. That's because though radiation causes ionization of atoms, it needs to be at high enough levels to affect molecules, and at high enough levels to affect cells, and at high enough levels to affect tissues, and at high enough levels to affect organs, which only then would be at a high enough level to affect the whole body. There are thresholds for dosing, and if we stay below them, we can prevent exposures from evading the body's natural repair pathways and moving beyond the cellular level to cause lasting tissue effects. My research is helping to identify one of these thresholds, looking at the eye and more specifically at the epithelial cells in the lens of the eye, one of the most radiosensitive tissues in the human body. Specifically, I'm trying to find a threshold for when exposures will lead to cataracts. Radiation is an essential tool that many people use for work. We want to ensure we're using it safely and allowing them to keep working. There are two main ways I'll be trying to find this threshold. First, looking at fractionated exposures will tell me if there is a different dose threshold for a radiation exposure that is delivered in a single acute dose versus one that is spread out over a longer period of time, such as an occupational exposure. Second, using low doses, I'm trying to identify where the threshold is. The only evidence that is available right now is from high exposures, where they have to then guess at what will happen in the low dose range. I will be generating actual data in this area. The ways I'm classifying damage are first direct damage at the DNA level, and then the indirect damage at a system level by measuring the levels of stress markers. This will hopefully provide information about the damage in an even more specific way. Right now, I've optimized multiple protocols for each of these markers. I'm exposing them to radiation and staining them to see what's going on inside. For example, this picture shows one technique. These are my cells normally, under phase contrast. And here I've added fluorescent labels. The blue fluorescence is the nucleus of each cell, and the green fluorescence tells me how many DNA breaks I have in a cell nucleus. Together, all of my protocols will hopefully support a threshold. What I really want you to take away today from my discussion is that radiation is an essential tool, and if we understand thresholds, we can optimize its use while keeping those exposed medically and occupationally safe. Radiation gets a bad reputation, but if I was to ask you this question again, I'm hoping my presentation today and the work that I'm doing will help change the image that comes to mind. Thank you for listening. If you have any questions, please feel free to email me.